Hello everybody. In the previous lectures, it was suggested that we might write, build and calculate functionals of the density. We will see here, and especially in the next lectures, that this idea of writing functionals of the density is indeed possible and can also be very effective. But let's take a step back for a moment. What is actually a functional? This is not a completely new concept, of course, on the contrary. But we would like, in this and the following module, to take a step back and formalize a little bit more the concept of functionals, calculus of variations, and functional derivatives, with a particular interest to a specific class of functionals, the functionals of the electron density, which constitute the main character, the crucial quantity, of the entire course on DFT. Let's start then our description of functionals with an analogy. If you have a set of points, for example, in the domain of real numbers like here x1, x2, etc., you can create a mapping with other numbers, for instance, real numbers. And again, this is just an example. Via a mapping tool that connects the x1, x2, xn into other numbers that here we call f of x1, f of x2, f of xn. This is nothing else than the definition of a function, a real function in this case, from and to the domain of real numbers. Well, with the same idea, I can imagine a realm of functions rather than numbers. Each one of these functions, for instance, can be a real smooth function. And now I want to associate a real number to each one of these functions, again via a mapping tool. This time we do not call this a function, but a functional, for it connects a function to a number. Actually, it could also connect a function to another function, but let's keep it simple for the moment. We have associated a number to a function, which is the simplest definition of a functional. Okay, but besides the definition, let's give an example. We have a function, a generic function f. Let's suppose we want to evaluate the integral of the function between a and b. Of course, this is the area here in yellow, which is a number. So we have actually associated a function to a number via its integral. So this is a functional, capital F, of the little function f. Very simple example. And I doubt you have ever called a simple integral a functional, but it can be seen as such. And the simple examples, that is, examples of something that you already know very well, but doesn't necessarily call it a functional, are endless. Let me give you another one. We have again a generic function f, and we want to evaluate f at a precise value, x0. This is equivalent to an integral of the function with the delta at x0. Again, we have associated a number to a function f. So this can be seen as a functional. And we can generalize this. Here we consider a functional built with a weight function w. The previous example is simply a particular case of this class of functionals. In DFT, we will meet this class of functionals very often, and they have a lot of properties. For example, this is a typical linear functionals. Why? Because if you take the functional of the sum of two functions, the result is simply the sum of the two functionals, of the single f1 and f2. By the way, can you imagine a nonlinear functional? Give it a go. In the meanwhile, I can tell you that there are a lot of different classes of functionals. Local functionals, built by an intermediate function g, for instance, or non-local functionals of two functions. An important one, in our case, is the total energy, which is a functional of the many-body wave function. Again, we associate a 3n-valued complex function to a real number, the energy. Finally, let me mention another class which will be of great importance. A functional defined via a function, here the Lagrangian, that depends not only on the function q, but also on its derivatives. The classical action here is an eminent example, but you will see immediately that this is a very common class of functionals. So let's see some examples of these classes of functionals in the specific case of the electron density. The first case could be the contribution to the energy given by an external potential. In this case, the functional is simply the integral of the potential times the density, so a local functional. The classical electrostatic term, or Hartree energy, is already more complicated. It is in fact a non-local functional. Let's move to expression for the kinetic energy, for instance. As you will see in the following, in the historical part, one of the first density functional is given by the Thomas Fermi approximation, in which the kinetic energy is a simple functional, a 5/3 power, of the electron density. A more complicated expression, still for the kinetic energy, is given by the von Weizsäcker, in which appears an explicit dependence on the density and the gradient of the density. So we will see and use, for the DFT course, all these functionals. But in order to deal with them, we still miss an important concept. You see, in order to manipulate functionals, you have to know how they behave, in particular when the function on which they depend changes. And when you talk about change, you talk about derivatives. So do not miss the second part of this module dedicated to functional derivatives. And for the time being, I say goodbye.